First of all, I would like to thank organizers for inviting me to this beautiful place back, and also for placing my talk so strategically. So from what I meant is that actually a lot of these points I wanted to make were made already by speakers yesterday and day before yesterday, so I got quite easy job. So what I'm going to, it's going to be a little bit messy and general talk. I'm not going to dwell on any specifics, but I would like to respond to this call of this conference, so understand when we can use textbook formula to understand the deviations from conventional Fermi-liquid, and when we have situations where we don't understand. And so, as I said, the work is based on many years of studies on wide variety of materials. And the point I want to make is that each case is quite different. So we, from one hand, cannot say we cannot put them on the same roof. From the other hand, I want to instantly claim that this technique allows quite quickly and instantly separate cases where we have an expected Fermi-liquid behavior from something that is not, it's beyond Fermi-liquid, and this point was strongly made by Peter yesterday, so showing the Q dependence of the Raman response function. So in this experiment, I'm limited to Q equals 0. So essentially, my discussion is going to be in subspace of what Peter spoke yesterday about. I want to also make a side remark that these days there is an inelastic X-ray scattering that allows to go to Q space and look for the Q dependence of the same properties. But over there are resolutions and etc. issues. Okay, so in the Fermi-liquid, in the charge sector, in the true Raman probe, which probes very low, very long wavelength excitations close to Q0, we really should see no signal. We should see no signal at low frequencies, at least in one band systems. No signals at low frequencies, and not even a plasmon, because the plasmon is suppressed by Q square term. So there should be really no response in Raman. Well, this was pointed out for many years until Platzman was on my memory discussing that with Aaron Pinczak, whom Peter mentioned yesterday as well, because in his beautiful fractional quantum Hall measurements, he sees quasiparticle excitations and collective modes in the Raman scattering, and Phil was saying, what the heck you are looking at? So what do you really see? In more complicated case, in multi-band system, all you can have is low frequency excitation, which comes from the sound modes of, and it's really limited by QV Fermi. And QV Fermi, because the Q of light is 1/100th of the Brillouin zone, it's really nothing. So even at large V Fermi, we should see nothing in the signal. Okay, Sanger pointed this out, 99, trying to explain Aaron Pinczak's data. He says that, well, it's a puzzle. No signal should be seen, but he claims that the puzzle is resolved, and the resolution was proposed by resonant Raman scattering, where you come in with a photon in resonance with interband transition, and then the signal is enhanced. And then you see single particle excitation, collective modes, and et cetera, et cetera. True, but I point out that the calculation was still done at finite k, at finite q, and the q is substantial. This is 1.1 kF. So at q equals 0, or very close to q equals 0, this term is also vanishing dismally. So now back to cuprates. So already the very first data mentioned by Peter yesterday, in all channels where people looked, they see substantial signal. There is a substantial continuum. Here it's measured at 2000 wave numbers. In my follow-up data, early data, we measured that to electron volt. We measured it further. What's shown here is a material which is YBCO at different doping. When it's an underdoped, there is a feature which resembles magnetic scattering. It's a 3000 wave numbers, 3J peak. It's comes from magnetic correlation. It's a two-magnet scattering, but so this that 4 curves depending on doping, and this dotted line is for optimally doped YBCO, and you can see it's entirely flat, flat to 1 electron volt, and I don't have that whole data, but we measured it further, it's still flat. And Peter showed that it continues to 2 electron volt, and etc. And this is general for cuprates. So this is BISCO, same material as was discussed yesterday, and well, there is this flat continuum at all dopings. And again, early on, it was proposed that if we assume that there are some kind of bosonic excitations with this polarizability, these properties, then we can derive this marginal Fermi-liquid, and that assumes also the Q independence. This test is a repeat only Q equals 0 test. And then we can, we are good, except that we don't know how to get that phenomenological theory. Now I want to say that this is not just a property of cuprates. So it turns out that after that, we believed initially that this is extraordinary, a very special case. But, well, anything I have touched out after that has a continuum. So calcium C6 is a 12-degree superconductor. You can think about that as a doped, heavily doped graphite. So that's the Fermi surfaces around K points, K and K prime points. And in Raman spectra, you see beautiful continuum, strong continuum. Those are two phonon scatterings, something that Dresselhaus studied in the 60s. But there is a continuum. There is a renormalization of this continuum in the superconducting state, but it's a different system, completely different system. Niobium diselenide has a continuum that keeps going on. NGB2 is so-called two-band superconductor. There's actually 4 bands in game around the 4 Fermi surface pockets, and there is a continuum. Red is normal state, and it keeps going. So those are phonons. There are some gap features, but the continuum is there. 1,3,5 vanadite was discussed yesterday and day before yesterday. It has this CDW transition. Above the transition, there is a continuum. Below the transition, you can see that the blue sky opens up, so the continuum gets suppressed. New phonon modes appear, as you would expect, because of the symmetries are broken. But But again, there is a continuum. Pnictides were discussed yesterday. Old story. So there is a nematic channel, which is this channel where we have the Fermi surface Pomeranchuk-like fluctuations. There is another channel which is orthogonal to that. In that channel, surprisingly, this is parent compound, there is no continuum. There is a phonon, but essentially there is no continuum. But in the nematic channel, there is a strong continuum which cleans up below the nematic transition. So below the nematic transition it goes up. So these are kind of classical fluctuations that we can understand and can describe. And they have been nicely described and explained. So, and that happens in all families of pnictides. So this is a europium compound. This is a 111 compound where also has that fairly strong continuum. And below TC, when the gap opens up and the continuum gets suppressed, there is no continuum. So this fluctuation becomes a very well oscillating collective mode. And this is just a nematic collective mode, in some sense can be put in context of even previous talk, where the Fermi surface is fluctuating. Okay, so iron selenide was discussed as a special case because iron selenide is interesting material. It has very, very low EF, very small pockets. EF is smaller than most of the energy scales. Complex phase diagram. So I'm going to discuss things at zero pressure, but with sulfur substitution, where this superconductivity, the structural phase transition, the nematic transition can be suppressed by putting chemical pressure, by putting sulfur in the system. Now, in the parent compound, right here, the resistivity, even below the TS, is linear. It's quite linear resistivity. So as the derivative of that, d rho dt, it's essentially constant. What do we see in Raman? In Raman, in the nematic channel, and this is the quadruple channel where we probe the nematic fluctuation, again we see continuum. This is 1/4 of electron volt. We see it below. So now in this system it doesn't, remember EF is very small. We don't get the continuum to many electron volts. It ends here at 1/4 volt. But if we cool the sample, then we see another feature, and this is the nematic fluctuation feature. And then below the structural transition, below this transition, the spectra cleans up, and there is no excitations anymore in the gap, at least in this channel. But now, interestingly, we have still linear resistivity. Now, this data can be described by constructing a self-energy, which is, well, by analogy to what Chandra was doing 40 years ago, I can build a self-energy that can fit the data. I change the scale to log to show everything. So the self-energy will behave like that. And the self-energy is essentially marginal at, and this is all in nematic channel, at high temperatures above the nematic transition, while below the nematic transition, in order to explain this very clean gap, I need to assume that I have this omega square behavior in the self-energy. So there is some kind of a crossover from one regime to another regime. However, there is still linear resistivity, and now I'm probing to quadruple channel, resistivity is optical, related to optical conductivity. It's in dipole channel, so it's probably not the same. How am I doing on time? Okay, very good. So let me say a few words about other systems and bring in an example where maybe we can explain where the continuum comes in. So if you take a system with strong spin-orbit coupling, and we know that the spin-orbit coupling is present on various scales in all these materials that I discussed, but largely was ignored. Then, well, in this very naive picture, the Rashba system, Rashba metal, depending on the doping, where is the doping level relative to this Dirac point, which you get in Rashba spectra, you will expect a continuum which is chiral continuum, because now the bands are spin polarized, we have a spin flip excitation, and there's going to be onset of the continuum at this energy and end of this continuum at this energy, and it should appear only in the chiral channel, which is A2 channel in this point group. And indeed, in the data, we do see this nice chiral continuum, which is related to this excitation. So far, so good. But then, if we again look for full symmetric channel, we expect nothing. We expect no signal. But we see again the continuum. We see the continuum, and moreover, we see beautiful collective mode below this edge of the interband continuum excitation. So we have a gap, and inside the gap, there is a collective mode. The collective mode must be a plasmon. In fact, we checked, it behaves like a plasmon as function of carrier concentration. If you change n, it behaves the same way. So we were very puzzled, because as I started, there was a statement, there should be no continuum, there should be no signal, there should be no plasmon in Raman spectrum. This is the case where we could find the way around, and in case of this Rashba system, with the presence of this three-dimensional, the sigma 3 K term, which is determining this deviation of the spins from the plane, so this excitation can be explained, and that was work done in collaboration with Surab Maiti. So this type of diagrams where now in the presence of this term, on this propagator, in the resonance regime, we can flip the spin. We get a coupling to this term, and in fact, the Q square drops away, because these vertices now are only proportional to Q instead of being proportional to Q squared in conventional physics. And now, indeed, it's an example where in Raman spectra, you can get continuum, but it's a very specific case. So the rest what I showed remains still a puzzle, at least to me, because, I mean, in my 40 years of experience taking the data in A1G, I, at some point, was avoiding even showing it in my papers because I couldn't explain the charge response in full symmetric channel, which is often dominating signal and completely unexplained. So I can stop here. I think that's my time.
In Raman, in A1 also, I think, you can, so you normally wouldn't see odd parity modes because of symmetry selection rules, but you would see the two phonon modes. which gives a broad continuum. I'm not saying that that is the continuum. I'm clear about it. But since there is a selection rule for electron hole excitations, as you say, suppose you would make double electron hole excitations. Would that be a way to work around this in the same way, actually, as this one?
No, because I mean there is a kind of there are many fundamental issues there. The first one is essentially the charge conservation. Well, let's say for one-band systems, it's very clear. For charge conservation, the excitation can only be rigid in each unit cell, and it prevents you to have any response at any frequency, even in resonant at Q equals 0. Right. So, and it doesn't matter whether you do it in second order, third order, whatever. So what matters is the symmetry of the end, and if that excitation is at Q equals 0.
There is just one caveat. I spent 10 years working on it.
Yeah.
Is the massive breakdown of the momentum conservation because of disorder.
Oh yeah.
But that is very model dependent. We could fit everything.
Yeah.
I'm very happy with it.
Yeah. Okay. No. If you plug in disorder, and we of course we all were doing. Yeah. But when you're explaining Aaron Pinzer's data on gallium arsenide, which has right, or YBCO that has mean free pass from one edge to another edge of the sample, I mean we cannot blame disorder.
There's a theoretical solution.
Yeah. Could you please take a microphone? The microphone. Okay.
Yeah, it's fine. I'm happy with the answer.
Yeah, Tom. Yeah, just a quick question. For the last part on bismuth, can you turn the A to G excitations off by changing the incident photon energy, or can you modulate them stronger?
Well, I didn't have it here exactly. So that is purely resonant term, and in fact, it's important that there is Rasba interaction in both the lower band and the intermediate band, and in that case, we get the enhancement. As soon as we move away from that, we lose that. Yeah, exactly.
Thanks.
Thank you for clarification.
Is there this continuum you see, can you make any connection with Peter's data?
Yes, I mean, as I said, it's a limiting case. It's a Q equals 0 case when I do the same material as Peter studied, BISCO, at any doping. I flashed that, 25 years old, right? It shows the same stuff, yes.
Let me ask you a question. Okay, this is about iron selenium. No, you know, when you go in the nematic state, you mix the B1G and the A1G channel. So somehow the gap that you see is just reminiscent of what you have in the symmetric channel. And, you know, with Andre, we worked this out a few years back, which is more natural explanation, not invoking marginal Fermi-liquid that, you know, it's a legitimate point of view, but we know that we mix the two channels, and the A1G channel, you have cancellation of spectral.
Laura, you are correct. So when you go to nematic, when you break C4, you end up in C2 phase. These two channels mix. That's fine. But what I'm making here is that in this quadruple channel, I have a clean gap. And I recover Fermi-liquid up to this frequency. I have omega square behavior.
But it's fine.
But
the resistivity is linear.
yes, that's exactly what we were saying.
Yeah.
But again, question is this. You said, sorry, you invented this question. You said that you put self-energy omega square and you describe gap phase. How can you describe it? It's a gap.
Yeah, exactly.
So,
Well, the point is that if you have omega square T square, you don't have signal in Raman response. That's what happens.
why?
Because
It's not density channel. So why don't you have a signal in Raman response?
Well, of course,
In density channel, of course, it will cancel out, and this is what we are saying, that non-density channel becomes like density channel. But that's how we get a gap. But if you just put omega square self-energy...
It's a quadruple channel.
Yes.
Well, what I'm doing just naive inverse problem. I'm looking for self-energy that can fit my data. And this is the answer.
Yeah, well.
Okay, but then the question would be where this self-energy is coming from. So in the sense that we took a point of view that was much more natural and trivial, which has to do exactly with the breaking of the symmetry, where you mix the matic channel and symmetric channel, right? And then the gap is just a manifestation of the cancellation that you were talking about during all the talk in the symmetric channel. So that was the real idea behind it.
Yeah. Maybe we should follow up.
Yeah, it's not the main part of your talk.
Yeah. Let's discuss that.
More questions? And we're good. Guys, for 1 second. Yeah, before you go for lunch, don't forget that today at 1:30 p.m. in this room, 2 of our best will do music performance. It will be Philip Phillips and Dirk van der Marel. So everyone is invited, and I'm sure the room will be full, so come in advance.